Welcome back. This brief lecture is about Zeroth Law of Thermodynamics. This is in some ways an unusual name. There are three important laws of thermodynamics. This zeroth law was chronologically, it was found later than the three other laws of thermodynamics, the first, second, and third law. But in some ways, this is more fundamental, in a way establishes the notion, the meaning of temperature. Therefore, it was called zeroth law of thermodynamics. So we'll try to get a historical sense why this is also important. So if you're all probably familiar with Galileo. He revolutionized, is an important person in history of science. Let's see what he thought about heat. To Galileo, so in some ways there is this question, is there an observation when there is no observer? Okay, in some ways, Galileo's views on heat is sort of related to this question. So what exactly do I mean? So Galileo, so it's good to have a sense for the time period when he lived. Okay, so this is around the time when he was around. So he imagined heat to be a response of the senses. Okay, so like physical pleasure, discomfort, and so on. Okay, so it's a sensation. Okay, so of the human body. Heat is a sensation. Okay, so effectively, there is no such thing as heat if there is no one to experience it. Okay, so it's a very interesting viewpoint. It looks unusual now, but at that time, the great scientist Galileo thought in this manner. So even there is this another big philosopher in those times, René Descartes. The Cartesian coordinate system. Okay, so it's named after Descartes. So he's also a mathematician, and he's most famous for this philosophical statement: "I think, therefore I am." Okay, so is an important philosopher. So even he thought in this following manner: that is, heat is just a sensation of the human body. Okay, there is nothing objectively called heat. So all this brings out the importance of measurement. Okay, instrumentation science and engineering is very, very critical. What kind of measurements can be made, the meaning of these measurements, and the consequence of measurements. Okay, so we will look at this more closely. So what is the zeroth law of thermodynamics? This is the statement. Okay, so if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. Okay, so there is bodies 1 and 2. Let's say they are in equilibrium independently with a third body, let's say body 3. Then body 1 and 2 are in thermal equilibrium with each other. So if this is the power of this statement is more clear, if the third body which we are referring to is the thermometer. Okay, so if that is the third body, so if body 1 is in thermal equilibrium with the thermometer, what does thermometer measure? It measures the temperature. So and if body 2 is in equilibrium with the thermometer, again measures the temperature, then we can take it for granted body 1 and 2 are in thermal equilibrium with each other. So what does it take to be in thermal equilibrium? All it takes to be in thermal equilibrium is the temperature should remain the same, right? So for example, if I have, if iron is brought in contact to copper and there are no internal constraints, so the lack of internal constraint for the flow of heat is called that it's called diathermal wall. Okay, there is a diathermal interface. Dia means through. Okay, so if there are no internal constraint for heat flow, heat flows from the hot body to the cold body till they get equilibriate. At equilibrium, the temperature is the same. Okay, of here in this case, iron and copper temperature. When the temperature is the same, we say they are in thermal equilibrium. All right. So this established the notion. So why is this very important? All right. So if supposing a temperature of an object, iron, let's say, which is at 60 degrees centigrade, is the temperature of this object is measured by a thermometer. And copper which is at 60 degrees centigrade, is measured by a thermometer. In both cases, the thermometer shows a reading of 60 degrees centigrade. Then you can take it for granted that when iron is brought into contact with copper, there won't be any heat flow. Okay, so it's very, very important. It establishes the important notion that temperature is an intensive quantity. Okay, so, and it is independent of mutual contact of body. I mean, that is the thermal equilibrium is independent of mutual contact. That is, iron and copper need not be brought in mutual contact to say that they are in thermal equilibrium. All it requires is the temperature reading by a thermometer should be, in this case, 60 degrees centigrade. If you know that, it's not necessary for us to bring iron in contact with copper to say that they are in thermal equilibrium. So this is a very important law, right? So in fact, you can ask the question, why is this, what makes up a law? Okay, so the meaning of laws. Okay, so we know what it takes to be a brother-in-law, sister-in-law. What does it take to be a scientific law? Okay, so if you say that this is of very fundamental importance. Okay, so this notion of measurement of temperature by a thermometer and this notion of thermal equilibrium is never disobeyed. Okay, this has an empirical validity. That is, in every experiment, if these notions are valid, and it has to be stated. Okay, so it is of fundamental importance to establish the meaning of temperature through thermometer measurements. It is important to state this concretely. Therefore, you cannot just take it for granted. Without establishing this as a law, the meaning of temperature via measurements by thermometer is not clear. Okay, so this has stated conclusively. This was stated. All right. So the person who is given credit to stating this law is R.H. Fowler. Okay, so it is in some sources. It is said that when Fowler was reviewing the book by Saha and Srivatsava, okay, it's a wonderful book. The second edition is supposedly in 1935. It is mentioned in Fowler's book itself that he stated this law in 1931. Okay, so in some other sources, for example, in Wikipedia ascribes this whole thing to Arnold Sommerfeld. That Fowler stated this law while reading the book of Saha and Srivatsava. Okay, so in some ways, this is probably the first book that came from this part of the world on thermodynamics. It's a very, very clearly written book. Okay, so it's there in our libraries. We can also find it elsewhere. Even now, it is of great utility. It is written in 1935. So he reviewed this book in Nature. Okay, this, as you might know, is one of the frontier journals. So let's look at the review written by Fowler on Saha and Srivatsava's book. So the authors of this book have written a most stimulating version of the old song. Okay, so how does he describe thermodynamics? Heat, a mode of motion. Okay, in the earlier time, in the early 16th, 17th century, heat was thought of as a flow of a fluid. Okay, the caloric theory of heat, which was disproved later. But the notion of, which is the current theory, is the heat as a as motion, okay, motion of molecules, okay. So which, when we talk about thermal energy, we are talking about the average kinetic energy of molecules, okay. So that's what we are talking about. So heat is motion as a mode of motion. That's the way he describes thermodynamics. It's very well written, rather in a grand manner. So he continues with this review. I will let you read it, but I will just highlight some parts of the review which he wrote in Nature. It's an excellent descriptive chapters on thermometry, calorimetry, and production of low temperatures, heat engines, gases, changes of state, elementary kinetic theory, and other topics. Okay, so note the time when this book was written. This was written in 1935. Okay, almost 100 years ago, 85 years ago. But still, if you take up this book and look at what it emphasizes on kinetic interpretation of heat. Okay, it talks about heat engines without reference to entropy. It talks about Carnot cycle, and these are all very fundamental aspects. Okay, so it which makes up the science of thermodynamics. It takes you all the way to very practical applications of engines, okay, diesel engines, steam turbines, and so on. Okay, so it's a wonderful book, well reviewed by Fowler. Okay, so you should take a look at this book sometime. All right, so it's very interesting. Have some correlations and speculations. Just so I was just noticing this when I was going through all these things. Fowler is the PhD advisor of Paul Dirac. Okay, Dirac is a pioneer of quantum mechanics. Okay, so he established many fundamental things in quantum mechanics. He's a Nobel laureate, given a Nobel Prize given to his work in quantum mechanics. So Dirac did his PhD thesis not in quantum mechanics. He did it under Fowler. Okay, so the central drama of quantum mechanics unfolded in what is called Solvay Conference. Okay, so there was a great debate between Einstein and Niels Bohr about the meaning of quantum mechanics, with the how things are measured in quantum mechanics, what is possible, what is not possible. All these things unfolded in 1927. I'm sure Fowler must have been informed, even though I don't think he was a participant of the Solvay Conference of 1927. So there's a famous picture. If you just Google Solvay Conference, this picture would show up. Everybody who's anybody in quantum mechanics is there. Okay, so it's the highest density of intellectuals who contributed to the development of quantum mechanics, all in one place in 1927. So I was in quantum mechanics. The measurements play a very, very important, very fundamental role. Okay, so the measurement of a system collapses the wave function. Okay, so indeed there is no observation without an observer. This appears like a vague statement, but that's all right. You have to really go and understand quantum mechanics and understand the importance of measurements in quantum mechanics to understand the statement thoroughly. Okay, there is no observation without an observer. That is, without an observer making a measurement, there is no observation in some ways. All right, so measurements play a very fundamental role in quantum mechanics. I was wondering whether I'm sure Fowler, even though he didn't work in quantum mechanics, he was aware of this development in quantum mechanics. So I was wondering, because of the importance of measurements in quantum mechanics, Fowler was preoccupied about the meaning of measurements, meaning of temperature, measurement of temperature using a thermometer, and its significance in thermodynamics, whether he was bothered about all these things. That's why he stated this as a law, as the Zeroth Law of Thermodynamics. All right. So these are all. It's interesting to go through how science, in this case, the science of thermodynamics, develops. So it also gives you a certain logic. Okay. So it's not that you have to introduce the subject chronologically, but also gives you a certain logic why things are the way they are. Right. let's end here and go to the next topic we'll be discussing is temperature and thermometry.